Welcome and thank you everyone for joining today's webinar. This webinar is co-hosted by the California Resiliency Alliance and Cal OES. It provides a winter weather outlook and an overview on the debris flow hazards from the recent wildfires. My name is Monica Stoffel and I'm the Executive Director of the California Resiliency Alliance, where the mission is to empower local and regional resilience through cross-sector information sharing and partnerships. Today's webinar continues a series of webinars hosted this year on seasonal weather outlooks and a series that we hope to continue into the new year. Recordings of past webinars can be found on the CRA website, and the Fall Weather Outlook webinar included an overview of some useful weather monitoring pages, as well as weather patterns to look for. So you can go back to that one and get a good insight on kind of how to do weather analysis and what goes on behind the scenes as well. Today's webinar is being recorded, and the recording link, slide deck, and links to resources will be shared with all of the participants who registered for the webinar in a follow-up email coming out later this week. We invite questions from participants. The Q&A will be managed through the chat feature. You can submit your questions at any time. They will be moderated and posed to our presenters. Questions that were submitted in advance have been collected and will be incorporated into the moderated Q&A. I will now hand it over to Abby Browning, Chief of Private Sector and NGO Coordination at the California Office of Emergency Services, for the introduction of our first presenter.
Thank you, Monica, and thank you to all of the work that you've done, as well as leading the California Resiliency Alliance, putting on these webinars and encouraging us to think beyond COVID and look at the other disasters that California faces and prepare for them. To make this very quickly, I'm going to do the introduction for our first speaker, but I'm going to make it short because I want to get right into the programming. We have two exceptional speakers today. The first one would be Brian Garcia, who is with the National Weather Service, serving the San Francisco Bay Area, based out of Monterey, California. He is a warning coordination meteorologist, and he is charged by Congress to partner with emergency management and other partners to ensure the best weather information possible is getting to decision makers to accomplish the National Weather Service mission and the protection of life and property. So I will turn it over to you, Brian.
All right, thanks, Abby, and thanks, Monica, for hosting this. And I am going to say just right out of the gate, I'm super excited to share the time presenting with Don Lindsay of CGS. So that's always really cool. And I know he'll get introduced later, but I just had to get that out now. All right. So we're gonna hop right into this, and I'm gonna for those of you who saw me present last time, you're gonna see some of the same information just updated. But I'm gonna roll through a lot of this, and then I'm actually gonna go on a another little bit of a web tour, because I know that since Don's talking about post-wildfire debris flows, I want to make sure that I hit a little bit on that as well, and we'll talk a tiny bit about that through this, and then I'll show you kind of what we use, some of our internal stuff. So anyhow, thanks, Abby. I am Brian Garcia, warning coordination meteorologist for the San Francisco Bay Area and Monterey Bay regions. So we cover 11 counties around here and about 8.5 million people or so, something like that. And then, of course, I have counterparts throughout the state. Throughout the state, we have 11 weather forecast offices from the National Weather Service that service California. Some of them, all they do is parts of California. Others bleed over into places like Arizona or Nevada or Oregon. So we're going to look back. I'm going to talk to you just briefly about the communication, look forward. So looking back, what we see here is the drought monitor. So this is this is the drought monitor as of December 1st. And actually, we are currently debating any expansion of the drought monitor right now for the next iteration of that, which I believe comes out this Thursday, actually. So we'll be looking at an expansion, and I'll actually I'll go dig in my dumpster here in a minute and show you guys what it looks like, a little sneak peek, because it's still only in draft stage. So this year, a lot of Northern California plunging into drought. So we have the extreme drought through the North Central Valley, and then we have severe drought through a lot of the other area, moderate drought going all the way down into Southern California, as well as abnormally dry dipping down into Southern California. Last year at about this time, we were abnormally dry across a bunch of different areas, but not across the whole state as a whole, because we actually had a significant winter. Since I showed last time I talked to you guys, I'm going to show what we've been doing so far this water year. So since October 1st, which is the start of the water year, and going forward into now, this is what we are at for the water year as it stands. So across the Bay Area, we have some 20% rain, 20% areas, but some areas are even in the teens. You start going farther south, you start seeing areas that are only in the single-digit percentage-wise in terms of percent of average at this point in the water year. So what this says is essentially we haven't seen enough rain yet this year. And you might see some little smatterings of higher amounts. Some of those are air data. Others of those are just areas where a really strong shower passed over. A couple of strong showers passed over and may have given a little bit more in terms of precipitation than even their neighboring sites. So by and large, we're well behind. So communication-wise, if you don't follow us, please do. We have been putting a ton of stuff on Twitter, especially about the red flag warning that was out last night into today, and the one that's not the red flag warning, but more potential heightened fire conditions as we go into Wednesday into Thursday morning. So we put a ton of information out there about that type of stuff. So El Nino, La Nina, normal conditions, what's what, why, who, and when, and how. Well, El Nino, just as a reminder, is the warm waters across the equatorial tropical Pacific slopping over to the east, so up against the South America and Central America there. So we get all those warm waters moving over there. We get all this thunderstorm activity, this convection sliding farther east as well. La Nina conditions are quite opposite. All that thunderstorm activity gets shoved up to the west, as well as the warm tropical waters. We got all this cold water coming up. Neutral is right in between. It's just kind of a happy sweet spot. It's kind of like Goldilocks El Nino. So in the sea surface temperatures, what we like to see is all of the reds over to the left, and we like to see the blues down here on the right and bottom right. That is the typical scenario we like to see. So everything's looking good, but we've got to compare that to what it looks like on average. So what's our average look? So we look at the anomalies to see those comparisons. And we've been seeing this huge swath of blue just encompass the equatorial tropical Pacific. And it's been that way for several months now. And it looks like even just in the last few frames, it's trying to weaken a little bit. And I'll show you the models. So we see that going into October, the measurements dropped us below the 1 degree C anomaly. So that means we're 1 degree C below what is normally there. So since we're down there, that means we are actually in a moderate La Nina. So we are in a legit La Nina territory. If we were just in the -5 to -1, -0.5 to -1, we'd be in a weak La Nina. So it looks like it's bottoming out sometime around our time now. And by the way, these 3-letter identifiers down here on the x-axis, OND is October, November, December, NDJ, November, December, January. So climatologists like to look at things in climate type scales. So that generally is like 3 months when we're looking at kind of the near term climate type things. So if we run all the models out and we see it kind of flatline through here, and then it slowly starts creeping up, even if we follow some of the faster models and just go a little bit faster, we're not coming out of La Nina until the February, March, April timeframe, and really more likely that March, April, May timeframe. This is very significant for our water for the year. So when we look at typical wintertime La Nina patterns, it favors a northern trajectory for the storms. So those storms favor a wetter and cooler Pacific Northwest and a drier and typically warmer Southwest. So this is the pattern that we've actually seen set up. We haven't been necessarily quote unquote warmer. We've been pretty average in terms of temperature over the when it's averaged over the course of a month. So we've been relatively average, but we have seen a very wet Pacific Northwest, and it's been trying to drip down into Northwest California, which climatologically speaking is Pacific Northwest. And there is a chance that we could get a front or two through here this month, but we'll see what we get coming into the Central Coast. That's about as far south as it looks like it goes. I was trying to find a graphic that said La Nina instead of weak La Nina, but rest assured, if it was just pure La Nina, this percentage would be more like 70 to 80%, and you'd see like 20% for this slice over here, and you wouldn't even see the 10%. So the vast majority of La Ninas have been dry for our state, while some have been normal, and I think maybe one has been wetter than normal. So the history tells us that it's generally drier in California with La Ninas, and this is just another way to look at it. So once we get into our seasonal prediction here, this is for the month of December. In December, the temperature on the left here, we have a greater probability, these are all probabilities, of being warmer than normal for the vast majority of our state. So the farther south you go, the greater the probability is. On the right, you're going to see precipitation. Precipitation, we have this the fancy EC here with the A meaning above, the B meaning below. That EC means equal chances, which is the meteorological equivalent of a shrug, meaning it could be either above normal, below normal, or near normal. So that's equal chances, essentially 33.3% chance of anything happening. So that's what we're looking at for December. So I have a feeling we're probably going to be dry for the most of our state. Like I said, we do see a couple fronts trying to get in down here by the mid to late month, but it looks like they're falling apart across the Bay Area and really just kind of die on the doorstep of Central Coast, not making it to Southern California. So now we're going into those 3-month stretches that climatologists like to look at for those seasonal type conditions. So December, January, February, this is the core of our winter. This is when we get the vast majority of our precipitation. And most of our precipitation comes in atmospheric rivers. Half of the average annual precipitation comes in that. So when we're talking about on the right chart there, we're saying like for far Southern California here, we're talking a 70% probability of being below normal. That's huge. The vast majority of the state, like 3/4 of the state, is greater than 50% chance of being below normal precipitation for this time frame, December, January, February, and above average temperatures. That's going to stand true for the entirety of winter. So once we get to January, February, March, continue to show below normal precipitation, above normal in Pacific Northwest. Remember, the La Nina patterns favored the Northwest. February, March, April, continued, vast majority of the state, 50% chance of remaining below normal for precipitation during this time frame. And once we get into March, April, May, we're starting to transition out of our truly wet season, or we've transitioned out of our truly wet season, and we get much more into our showery type regime. So just passing showers type thing, as opposed to big beastly fronts that bring a lot of precipitation. And even so, in this March, April, May timeframe, we're still looking at a greater than 50% probability of the state of California, the vast majority of the state of California, being below normal for precipitation. That's going to put us in a world of hurt for drought conditions by the time we get to next summer, because last winter we only had about 50% of our average annual precipitation across probably at least half the state. I know Southern California had a bit more, but a bit more in Southern California means they got like 1/10 of an inch more. So it's still very, very, very dry, and that's going to propel us into much deeper drought conditions as we get into next year. So that said, despite thinking that we're going to be dry for the vast majority of winter, we still can and probably will get a whopper of a storm someplace. And when we do get that whopper of a storm, we've got to be ready for it, because it can bring the impacts to us. And one of the things, and I think that's my last slide, one of the things I wanted to show you really quick is on our web, not on our public facing webpage, just our internal webpage that we use in office. We've been working with Don Lindsay and his crew up at CGS, as well as others at USGS, to deal with flash flood thresholds for debris flows in our service areas. So our service area is the entire Bay Area minus Solano County, and then down into San Benito, Monterey, and Santa Cruz counties. So we have established thresholds with our partnering agencies at the GSs for the Monterey Bay areas. So these burn scars, that the River, Carmel, Dolan, CZU complex, as well as established thresholds for the SCU. And we're still working, we're still kind of making sure that we got the thresholds right up in North Bay for the LNU complex as well as the glass fire. But essentially, if we're expecting rainfall rates of these to occur over one of the burn scars, this could potentially trigger a flash flood warning for debris flow. That means we'll have a flash flood watch out ahead of time saying, hey, there's potential of this happening. And then once we see something coming in either on radar or we see it on rain gauges that are out ahead of the burn scar, between the burn scar and the storm, if we see something there, then we will be issuing a flash flood warning. That flash flood warning for debris flows will trigger an EAS, so an emergency alert system, and a wireless emergency alert over your cell phone. So you'll get it TV, radio, and cell phone. So make sure that you have redundant forms of communication available in case you are susceptible to some of these areas and you are subject to this area and you have needs in this area. We have burn scars throughout the state. All of our forecast offices have done something very similar. These are internal numbers that we typically don't share with the public, so please don't just like go out to the press with all of these. This is something that we watch very carefully, but we're also not, it's not hard and fast. If something looks like it's going to be close, then we might be issuing something anyway. If something looks like it's a little over, and we've seen that multiple times through the winter and we know nothing has slid so far, we might be nudging the numbers upward. So just something to keep in mind there. The other thing I want to show you really quick, and let's see if I can do this. You guys get a peek into a government federal email trash box. Let's see, so I told you I can give you a little sneak peek. Again, these are all draft, but you can see here in the bottom left corner here, we're talking about expanding the drought a little bit deeper. So instead of being D0 down in this coastal southern part of California, we're talking about going D1 and even bringing that D1 down into Monterey and stuff, and expanding the D2 a little bit more. So there are a lot of moving parts. There are a significant number of partnering agencies out there that we work with and that we deal with. So with that, I will pause and say, hey, Monica, is there anything in the chat that I need to answer?
So one question that we have had come up, and for others, if you do have questions, feel free to put them in the chat. We may collect them and do a larger Q&A at the end, is in regards to hail warnings. I know that was something you hadn't really touched on here, but a question that came up of hail warnings, how far out can people expect getting them? And is that something we might be experiencing this winter?
Sure, yeah, in terms of hail, so those will typically come with thunderstorm activity. And if it's going to be a severe type event, meaning that hail is 1 inch in diameter or greater, then we'll probably have some kind of severe thunderstorm watch out ahead of time saying, hey, the conditions are looking prime, tomorrow for these types of conditions to occur. And then we literally wait for those discrete cells to really start to pop up. So what you'll end up getting is if we issue a severe thunderstorm warning for large hail, those will probably come with anywhere from 0 to about 30 minutes of lead time. So you'll have very limited time to react to that. And those will trigger severe thunderstorms warnings will trigger the emergency alert system as well as the wireless emergency alerts on your phone. So hail is something that we do watch. The problem, of course, is once you get to the northern half of the state, I should say like from the Central Coast northward, and probably more towards the coast, the interior gets some big hail, but we get really small hail. We get pea-size hail. We don't warn for that. So what you'll see from us is you won't see it. You won't see an EAS. You won't see a WIA. What you'll get is information through our social media channels, and you might get a special weather statement coming out of our office, but that doesn't trigger any sort of alerting protocol. So the key with that is just to make sure that you're paying attention to what the forecast is, because we will highlight it in social media that the threat is possible, and then make sure that you pay attention to what we're putting out as well through a number of channels. I mean, you can watch our website directly. If you have some way to bring in some kind of feed to feed your own system, we have all of those APIs available. Or you can watch something like Weather Underground or weather.com or something like that, because those will pop up on there as well. Me personally, I have a couple apps on my phone that I just nerd out on. So yeah, so that's how we do hail.
Thank you for that overview.
You're welcome.
On hail. And we will hold other questions because they mix in a little bit more, I think, with the next topic of debris flows, and do a larger Q&A at the end. Abby, I hand it back over to you to introduce our next speaker, and Dawn, I will hand presenter mode over to you.
Thank you, Monica, and thank you, Brian, for that presentation. I haven't decided if it's good news or bad news. I haven't made up my mind on that, because I could see positives and negatives out of both of those things that you mentioned. But
yeah, it's definitely both.
Yeah, it's both. And we're going to learn about a piece of that right now. So I'm going to turn this over to my colleague, Dawn Lindsay, who is with the California Geological Survey. Dawn is based up in Redding, which is about 3 hours north of Sacramento here. And he is lead of the Forest and Watershed Geology Program. Dawn performs post-fire assessments as a co-lead on the state watershed emergency response teams throughout California, and does post-fire monitoring in collaboration with scientists from the USGS and the University of Nevada at Reno. So Dawn, take it away.
Great, thank you for that introduction. I appreciate it, and great presentation, Brian. That was well done. The one positive that I got from your presentation related to the setting that we have developed with all the fires within the state is that it would be nice if we don't get walloped by a heavy winter, just to allow these slopes to kind of meter themselves out this winter. So that was good news. I am not looking forward to potential drought conditions, though, leading into the future. So thank you. I assume everybody can hear me okay. If I can just get someone to acknowledge yes, that would be great.
We can hear you perfectly.
Yes. Great, thank you. And you should be seeing a title slide with my name and the title of my presentation today, which is titled Post-Fire Debris Flow and Flood Hazards.
We can see that one clearly.
Fantastic, thank you. So this next slide is a slide that provides an outline of my presentation. First, I'll talk about post-fire effects, how they're related to triggering erosion-induced debris flows and flood flows. And with flood flows, I'll rope in bulked flood flows that include hyperconcentrated flows. I'll then talk about post-fire models that we currently use to predict post-fire hazards related to debris flows and flood flows. And then lastly, I'll talk about monitoring program that's been initiated to test models and to improve our ability to predict post-fire hazards. What I'm not going to talk about is in-depth assessment of our current burn scars and the hazards associated with them. What I would rather do is point you to the Watershed and Emergency Response Team reports that are produced by a group of state agencies, including CAL FIRE and CGS. And the Watershed Emergency Response Team reports are produced for generally every fire that's recognized as having a hazard to both life and property. And once finalized, those reports can be obtained through Cal OES. So I'm going to throw that out there. This is this presentation is generally geared towards general knowledge of post-fire effects related to debris flows and flood flows. So let's take a look at post-fire effects. And to do that, I'll take advantage of this figure that Hyde et al. Produced in 2014. And on the left here, you see as fire severity increases, we go from 0 to positive. We get a reduction in canopy cover, rainfall attenuation, surface cover, surface roughness. These reductions generally result in increased flow that then when you have increased flow, you get thicker soil, water depths, both as sheet wash and once it's concentrated in channels that can generate higher shear stresses on the hill slopes that can mobilize sediment and debris into debris flows. So looking at debris flows and specifically, what we're mostly concerned about is erosion-induced debris flows in a post-fire condition. And that's a result, again, of a reduction in the canopy and an alteration of the soils, leading to hydrophobic soils and soils that are have a sealed component that prohibits rapid infiltration. So you get rapid runoff. And here's a great example of a headwall swale. This headwall is within the Thomas Fire footprint in Santa Barbara County above the community of Montecito. And you can see that this slope was burned at moderate to high and was subjected to a significant storm event that dropped a high intensity, short duration storm or rainfall onto the slopes that rapidly generated runoff that converged into rills, and then those rills and bulk flows entered first order drainages. And you can see that once concentrated in the drainages, all of that water that's sheeting off the surface and is bulked from the immediate rill has exceptional strength power that can further scour out the channels right down to bedrock, which is the case here. You can see basically all the previous colluvium that existed within these low order drainages has been scoured and entrained into rapidly moving debris flows that propagated downslope while it was being in the confined environment of the channel system. And then it poured out into the community of Montecito downslope of Fan Apex that is on the upslope side of the community. And it had dramatic effects. The debris flows that impacted this area had enough power to move house-sized boulders. It dislodged houses off of its foundation systems. You can see the foreground here shows a flow path that exposed the foundation of a house that once existed here and carried it down slope. And of course, the power has enough to entrain automobiles. These debris flows can occur rapid and can have a high magnitude of devastation downstream. In this case, many of you are familiar with Montecito, and 23 people lost their life, unfortunately, in a post-fire debris flow condition that occurred in January of 2018. So I just mentioned debris flows, the erosion-induced debris flows. Now I'll switch to post-fire flood flows. And I've already described briefly how you can get more rapid development of runoff from a pre-fire condition. So this blue hydrograph shows what you would hypothetically get under pre-fire condition, where you have a lot of the vegetation attenuating flows. And then if you remove that vegetation, we get a flow occurring more rapidly and with a much higher magnitude in the post-fire condition that can result in flood flows. And not only does it impact the overall magnitude, or in what we refer to as the discharge, it can also increase the overall volume of total flow within watercourses. Those high discharges and high volumes amount to flooding in channelized areas that can take out, and as an example here, I have two examples, one from the Carr Delta fire in Northern California, where crossings were overwhelmed and washed away, and flood terraces were occupied by floodwaters impacting local private residences. In Southern California, in the Holy Fire, we had many of the basins that were subjected to moderate to high burn severity generated rapid runoff that entrained a lot of woody debris. Some of the debris, this is low water abandoned railroad trestle. And after a storm event in early December, this trestle was overwhelmed by flood flows and debris loading that resulted in the trestle being removed from its piers and transported downstream. Now we'll switch to modeling. We'll talk first about erosion-induced debris flow modeling. The debris flow model that we rely on is one that Dennis Staley et al. Published in 2016, and we've referred to it as the USGS debris flow model. What this model does is it predicts, it's an empirical model that is built on 4 input parameters, being one being slopes greater than 43% burned at moderate to high soil burn severity. Second, the change in vegetation measured by the degree of reflectance. This is called the difference normalized burn ratio. Thirdly, a soil erodibility factor for the fine-grained sediment. And then lastly, the short rainfall, short duration rainfall intensities that's this slope's subjected to. These are the 4 variables or factors that go into Dennis's empirical model that provides us the ability to predict the likelihood or probability of a debris flow occurring within a given basin. Now, Dennis followed his 2016 paper up with the second paper in 2017, where he took a look at his model and compared it against other models, as well as did a sensitivity analysis, which I find very informative. And with this sensitivity analysis, it tells us what variables have the most effect on driving the outcome of the model. And as you can see, the probabilities on the X or on the Y-axis increase and are most sensitive to rainfall accumulation. Sensitivity is on the X-axis, by the way. So rainfall accumulation, or the storm intensity, is the most critical component, followed by the slope steepness, followed by the burn severity, and then lastly, that soil erodibility factor is the least sensitive. So the take home here is it's very important that we, that rainfall drives a lot of the probability in generating debris, post-fire debris flows. This is a product of running the USGS model, and what it is describing here is the probability for individual segments having the ability of triggering a debris flow under a storm event of 24 millimeters per hour over a 15-minute duration. So what we see here is these first-order drainages that are burned probably above moderate and are steep they have a high probability of triggering debris flows. And then as you propagate down slope, as you increase the area, and you start to include more areas of less gentle slope and possibly areas that aren't burned at moderate to high burn severity, what you see is a slow reduction in the overall probability of debris flows being triggered. And this is fairly common. Where at the outlet down here, before you enter the built environment, you see we've slid from 80 to 100% probability in the headwaters all the way down to 40 to 60% before the built environment, and that's fairly common. Where you can get this data, again, this data is from the USGS debris flow probability model is generated and provided to the general public for fires at the USGS webpage. The address is on the top of the page. Basically, you can scroll through and identify the fire of interest and pull the data up and go through it. In the USGS model, and for time reasons, I didn't describe it to you in detail here. Beyond just the debris flow probability model, there's also debris flow volume model that predicts the volume of a debris flow should one occur, as well as other parameters such as watch streams that have a high increased likelihood of generating flood flows and possibly debris flows. Next, I'm going to shift gears and talk about post-fire flood flows. There's a multitude of different ways in which we predict post-fire flood flows. They range from involved hydraulic models using an adjustment to the curve number, such as HEC-RAS, or excuse me, HEC-HMS, to other more elaborate physics-based models, including the kinematic wave method, to more simplified models that resemble the Rationale method, where you increase the runoff coefficient and decrease the time of concentration, to empirical-based models, which are probably the most common that we apply, which generally result in the use of a multiplier to pre-fire flows to approximate post-fire flows that account for both increased runoff and bulking. Now, what I've done in this graph, this is for the CZU complex. This is a number of basins down here on the x-axis, where I've applied a number of different models to predict runoff. And so the y-axis here, we have peak Q in cubic feet per second. And you can see there's a wide spread in the data, which is worth mentioning and worth acknowledging. There's a lot of room to be done in refining our ability to predict post-fire runoff. Just for disclosure purposes, the maximum spread generated by these brown and green methods, these are generally only applied to methods that predict high concentrated flows like debris flows, where these other methods down here in the 1000 CFS and less category, these are generally for flood flows of lower concentrations of sediment. So these would be flood flows and hyperconcentrated flows down in this area. To further illustrate where we're at with the science in predicting post-fire flood flows, I'll reference this figure that Brent Wilder produced in his research in Southern California. What this graph shows is a plot of the absolute percent error looking at the predicted post-fire flows against measured post-fire flows. And you can see that overall, we missed the mark between 52% in the Santa Ynez range, all the way up to 500, say, to 800% in the Santa Ana range here. So again, a widespread in data in showing our ability to predict post-fire flooding. And then lastly, to illustrate this, is a study that Joe Wagenbrenner did in 2013 as part of his PhD dissertation. What this graph shows is a rapid decrease in the overall time of concentration from pre-fire to post-fire conditions. It went from roughly 6.7 hours all the way down to 20 minutes, which is a huge drop. And then looking at the unit flow, peak flow per unit area on the graph to the right, we see from pre-fire conditions a significant increase to the post-fire condition. And this increase accounts for about a 45 multiplier of around 44 times the pre-fire condition. So again, big range in magnitude of flows predicted by the various techniques. So to look at how well our monitoring our different models to predict both post-fire debris flows and post-fire flood flows, CGS, along with others, including the USGS, the US Forest Service, and universities that include Fresno State University, University of Nevada, Reno, have instigated a post-fire monitoring program. This map was produced last year and includes a list and graphically the spatial location of all the fires that we've have started a post-fire monitoring program. Now, I can tell you, with all the fires that we've had this year, those also are being monitored. And so this graph and figure will increase as time progresses. What the monitoring program consists of is developed by the USGS, and that we are, along with our partners, are implementing. It generally consists of installing a dense network of rain gauges, both standalone tipping bucket rain gauges and telemetered weathered stations, along with doing in-field measurements of soil infiltration. We then also install pressure transducers in the channel to look at both the timing of events relative to the peak rainfall, as well as develop flow hydrographs or rating curves that we can back calculate a flood hydrograph at key infrastructure. In this case, we have 2 stilling wells with pressure transducers installed at the footing of an arch culvert. So taking that kind of data into consideration and plotting it, this is for the Carr Fire in Northern California. This graph shows peak 15-minute rainfall intensities in the upper part. The debris flow model indicated to us that on a fire-wide average, if this threshold was exceeded, right around 30 millimeters per hour over a 15-minute duration, if that is exceeded, we should expect a 50% chance or probability of debris flows being triggered. I can tell you that, as this graph shows, that threshold was exceeded 13 times, and we did not identify any debris flows being generated. So preliminary results indicate that the debris flow model in Northern California, where the Carr Fire is over predicting the hazard. Also in the Carr Fire, we use the same monitoring program to establish a rating curve and look at runoff relative to rainfall events. So again, in the upper graph, we have peak 15-minute rainfall rates. The horizontal red line indicates the 1-year return interval rain rate over a 15-minute duration. And what you see in the bottom graph is the hydrograph where you have time on the x-axis and discharge plotted on the y-axis. This is the runoff hydrograph that we mapped over the winter period. And you can see that in some instances where we had very sharp, high intensity rainfall events, we had very high runoff responses. And in this case, for a rainfall event of just over 1 year, so we would expect this rainfall to occur annually, we generated a runoff event that was well over a 50-year RI event. And in this case, it calced out to be about an 84-year return interval event, which shows kind of the magnitude, again, of fire effects on runoff. So that I'll summarize by saying that there's, the need to improve our existing post-fire debris flow and flood flow models. And through implementing the current monitoring program, we hope to obtain a better understanding of post-fire effects to improve our predictive models. And then also, to add to this summary, I would reiterate that if you're interested in getting post-fire hazard assessment data, so I would refer to you to look into obtaining a copy of the Watershed Emergency Response Team reports for your particular fire of interest through Cal OES. And with that, I thank you very much.
Don, thank you very much for that presentation and kind of really that understanding of what are the risks around these debris flows, what does it mean, where are the triggers, what are the variables that have the greatest influence on the risk. One question that has come up is, what type of specific information in regards to debris flow risk to a city or town is available, or is that too granular for this type of analysis?
Using the best way to get at that information is to refer to in the state of California, we do what are called Watershed Emergency Response Team assessments, and those are post-fire assessments, again done by a group of individuals with specific talents in doing that type of assessment, and it includes members from a variety of different state organizations. I would say that if there is an area or a community that you have concerns with, more than likely that area has already been assessed and a report generated that is available through Cal OES. Those assessments take into consideration the information that is derived from the USGS model and other models, and include post-fire debris flow hazards, flood flow hazards, rockfall hazards, and all known hazards get assessed and reported through the Watershed Emergency Response Team reports.
Hey, Monica, this is Brian. I'll chime in with that too. And it's really important for people to have access and the ability to be able to contact their Office of Emergency Services within their county. I know in Monterey County, they've put together a great website that lists out those values at risk and shows and different areas that are potentially at risk, and they help go out and talk to people as well. So they try to get out and go door to door. Santa Cruz County is the same way. They actually went out and went door to door and talked to people who are in a risk area. So get in touch with your Office of Emergency Services within your own county.
Great advice.
Both of those responses, that is really good information. And kind of playing off of that, Don, you had mentioned the USGS post-fire debris flow hazards website. The CRA has actually created and kind of pulled together some of those resources and created a website on post-fire debris flow quick links that pulls together some overall resources, but then at the county level pulls through links directly to the USGS maps. And in other cases where like there's the U.S. Forest Service soil burn severity maps, the Bayer reports, I think the Cal OES, here's the Watershed Emergency Response Team evaluation for the Hennessy Fire. And as more of those reports are coming out, more will get added here, and they're broken down by county and kept for the past several years. And I think one of the questions that did come up was for the mayor's fire in Sonoma County, and that one is on here. If you scroll down to Sonoma County, it'll take you over here to this link. And so you can see the debris assessment. Do you want to quickly talk a little bit about what this shows and the different options and layers that they have here?
I would be happy to. Is this live or is this?
This is live.
Okay.
So I can click around if you want me to click around
Okay.
somewhere, or if you want me to hand
if you just scroll up so that we can see the explanation in its entirety. Just, I mean, I guess down then. Apologies. Yeah. Yeah, there we go. So see, that's perfect right there. What this is a link to a fire on the USGS website, and by default, what they produce when you click on the fire, you'll see this figure here that's kind of half cut off. But what that shows is the fire perimeter. Thank you very much. Perfect. The fire perimeter, as well as basins with their predicted debris flow probabilities identified. The black dots at the bottom of the basins, that's what we refer to as pour points. Basically, at each one of those black dots, the basins are evaluated and the probabilities are generated looking at the contribution area upslope. And again, looking at those 4 parameters, the model will predict the basin probability. So we can see that there's a couple of basins here that looks like there's 3 basins right in the middle that are at 60 to 100% probability of triggering a debris flow under a specified storm having a 24 millimeter per hour intensity over a 15-minute duration. And that's the standard reporting method that the USGS provides. And if you scroll down a little bit, see the material below the figure.
This is all the way down on the page.
Okay.
Download.
So normally yeah, there we go. That's what we want. I think there's a delay, that's why. But now we see the download, which is very critical. And I see there's some questions in the chat regarding where I mentioned that there's also a debris flow model results that quantify the magnitude of debris flows. And that model at each one of those pour points will predict the volume of anticipated debris entrained for each given debris flow. And that information is great. There we have the predicted debris volumes outlined here. So you can see there's a wide range. Generally speaking, it's a couple orders of magnitude for each break. Each of those 4 segments differ by quite a bit. But that shows you the kind of data that's obtained through the volumetric model, the Gartner 2014 model. And then, so they allow you to toggle through the basin hazards. You can go to the segment volumes also, the basin hazards, which is a combined hazard showing low, moderate, and high. What that is if you go to the basin hazard, thank you, right there. What that is basically a combination of, in a decision matrix of the range of probability on one column and the range of volume on the x-axis, and you combine those two to assess what the hazard is for the basin. So a basin with a high likelihood of triggering a debris flow and a high volume, obviously it's going to be high. In some instances, though, you may have a high probability of having a debris flow, but the volume is going to be so small, it may, in fact, turn out to be in the moderate range and not high. So there's that logic, and that's all disclosed in the supporting literature that the USGS provides. If you scroll down, you can also gain access to the data yourself, and inside the database, you can download it. It gets downloaded as a zip file. You can uncompress it, and all of a sudden you have all of the shape files. You have data there for all the input parameters used in the model. It's a fantastic resource that we rely on, that the USGS has developed. So I would say, for those who are interested, you can explore this, but I would also caution that it's easy to go into this model, get a look at the model results, and then have the desire to immediately apply them as reality on the ground. But this is a model. So in some areas, the model performs better. In some other areas, the model doesn't perform at all. And so that's where I caution the blind faith in this model, and would encourage folks to go to the work reports and look at the description of the work reports and the data that's presented and distilled in the work reports. I know that was long-winded, but I saw a number of questions pertaining to the USGS model.
And I think this provides kind of that great recap and ending point for this of here's resources to use, careful somewhat on the application of it, because it is a model. It is not reality in that sense, but it is very powerful in being able to use and being able to access that shapefile. And if you have GIS capabilities within your own organization, overlaying it, looking at what the impacts might be, you know, doing scenario planning for impact to facilities or employees. And then the other page the CRA has pulled together, also kind of referencing Brian's presentation, is the weather quick links. And part of this one also has a lot of links to many of the El Nino, La Nina resources that Brian shared, as well as a number of other ones. We are at the top of the hour, so I do want to kind of wrap up, be respectful of everybody's time. Thank you, everyone, for joining, and especially a big thank you to both of our presenters. Again, a follow-up email will include the webinar recording as well as some resource links and slides. This concludes our webinar for today, and thank you for your participation.